Okay, we're recording. So here's where we were last time. We were talking about what to do if the domain for your double integral is not a rectangle. Now, first point of order, can we even define double integrals if it's not a rectangle, right? We wrote down some very carefully defined formulas to define double integrals in the first place. If it's not a rectangle, all that crashes and burns. Can we do it? Does it make sense? Bunch of formalities, not our problem, Math 531, but yeah, totally. And what remains is you can still view a double integral, even on a non-rectangular domain, as being what you get when you chop it up into little pieces, and then on each little piece you multiply some integrand times area, and then you add them up. So conceptually, it's exactly what you would hope it would be, and it all works fine for our purposes here. Okay, so the next question we entertained was, can you write it as an iterated integral? And the answer was, yeah, everything works fine. The only new feature is that the inside bounds become functions of the outer variable. Right, and we talked that through last time because it basically boils down to it's a matter of looking at the shape, and you realize that these points that represent, for example, in this case, where our x integral starts, like at a point like that. Well, it's, the x coordinate of that point is going to depend on the shape of that curve. And so you're going to get different values for different y's. And so, said differently, it's a function of y. Okay. All right, so that's about where we left off, and I like to make the observation that, here, the picture that we've drawn here, we have this third dimension, we have this z-axis. Why did we draw a z-axis? Well, because z represented the function that was my integrand, and sometimes it's nice to draw that for whatever purpose, but the integrand's not in question. We already have an integrand, presumably. We're just trying to figure out at this point what are these inner bound functions, and the integrand doesn't have anything to do with that. So the nice little insight then is as you're trying to figure out these inner bounds, you don't need to draw the three-dimensional stuff. All you need is to draw the domain. So here's that same picture now. This is the domain, same domain. Right, and as I slice it up, and if you like, you can think of it as, I'm slicing like I've got a solid here, like people are comforted by having a graph, and you can, see the integrand being the height, and you're slicing, but all that really matters is what's happening on that slice in the domain. And so what that looks like over here is y varies like so as y goes from C to D. And then for any one of these y slices, let's see here. For any one of these y slices, for example, for that y slice, now again, you can think of that as being this y slice over here. Right? And so, we start at one point and we end at another point, and thus giving us our x bounds. Okay, well, yeah, but I can see that over here too. We're starting at that point, we're ending at that point, and that gives us our x bounds. And it's such an easier picture to draw. Here, drawing only the domain. We're not drawing this unnecessarily complicated three-dimensional picture, one dimension of which we don't even make use of. Right? So I think this is a really important point. You only draw the domain. And the process by which we're going to get these bounds is a very particular process. For example, this lower bound here, that lower bound represents the start of my movement along this y slice in the x direction. In other words, this lower bound for x comes from, well, it's the x coordinate of that point. That point is on that curve, which is going to have some equation. And now let's just remind ourselves, what are we actually doing here? Well, this thing that I'm trying to find, right, this a of y is a value of x. So I just need to then solve for the appropriate variable. I'm going to solve for x because this is an x coordinate. I'm going to solve for x in the equation of the curve that defines the point that is where my bound came from. So this is sort of the connect the dots of how we're going to connect the question of what is the lower bound to an answer of some algebra that I can do. And let me show you how this works in practice. Was that yeah?
Good question. Because we're only working with like the domain, does it just mean that you're holding like the z-axis constant?
No, it's that the z-axis is a visual aid that we don't have any use for. Right, so I've made this observation that when you're doing a double integral, right, the double integral is on a two-dimensional domain. Mm-hmm. We made this z-axis up. Okay. That's our little creation for our sort of highly questionable purposes, okay. Right? And so, don't draw it if you don't need it, okay. Right? Because the double integral happens on a two-dimensional domain. Okay. Yeah, does that make sense? Mm-hmm. Yeah. Okay. All right, so let's do one. This again is going to be the guiding succession of connect the dots ideas that we're going to connect. We're going to identify what bound we're interested in one at a time. What is the corresponding point? What curve is it on? What's the equation of that curve? And then solve for the appropriate variable. Okay, so here we go. Let's see. Let me full screen. There we go. Okay, so we've got here 3 given points. That gives me a triangle. My domain is the triangle. Solid triangle there. Right, there's our domain. We want to do an integral on this domain. Now, I'm going to gloss over where this double integral came from because it's not really what we're interested in right now. This could represent any number of things. Maybe I'm computing the amount of mass in this triangle, and maybe x plus y represents mass per unit area. Or maybe we're computing a volume, or maybe we're computing the amount of work it takes to blah, blah, blah. Not what we're interested in right here, right? Where I'm going to assume we have a double integral for whatever reason, and the question is how to write that as an iterated integral. So, for no particular reason, I'm going to do dy dx. I'll do dx dy on the next page. So let's see here. Let's think about our x slices. Remember, our slicing process is always outside in. So, okay, well, our x slices, as I go in that direction, this is what my x slices look like. And let's think about where's the first one and where's the last one. The first one is here. It's like a little micro slice that doesn't have any height, right? But that's the first little teeny tiny little slice. That's clearly at the origin. What is the x coordinate of the origin? Well, no fancy reasoning required. Sometimes it's really clear, right? The x coordinate of the origin, 0. No problem. Let's talk about the upper bound. Well, the last slice, as I continue going along, our last slice is that, which again, we got lucky. It's literally the equation x equals 1. So obviously then my upper bound is x equals 1. So say you get lucky sometimes if it's really perfectly obvious from the picture what the bound is, then you don't have to play any fancy games. Okay, now we're going to set an x. We're going to imagine on that x slice now, we're going to ask what are the starting and ending values of y. And here's where we're going to use this process. Okay, well, let's see. The lower bound for y comes from that point. Just see, right, in as I go through this in the y direction on that x slice, I start here and I end there. So my starting point is that point. That point, let's see here, let me clean up the mess a little bit. That point is on that curve. Conveniently, that's a really easy equation to identify. Right, so back up to here. We identified which bound we're looking at. We identified the corresponding point. We identified the corresponding curve. We've written down the equation. And now I just have to solve for what I need. And let's remind ourselves, though, it's easy to move too quickly on this kind of thing. So you want to, don't go so fast that you inadvertently do something that doesn't make sense. Let's remind ourselves, what are we looking for here? I am looking for a value of y. So in this equation, I need to solve for y as a function of x. And y as a function of x there is this, and that is our lower bound. Let's see another one. Let's see the upper bound. Let me just clean up the whole thing. Okay, so again, for a particular value of x, there's that x slice. That's how we move along in the y direction on that x slice. The upper bound for y is going to come from that point, which is on this curve, which has this equation. Now, how did I get that equation? It wasn't given to us. Well, yeah, okay, but they gave us these points, and the picture just, by the way, you really need the picture for this. The picture tells you what's happening, right? And I can see that the curve that defines this point that gives me my upper bound for y is the curve that's between these 2 points, because I see the picture, right? And that's how I knew to pick those 2 points. Is everybody good? You can't do this without the picture. It's so hard to do this without the picture, I'll say that. It's almost impossible. Okay. All right. So again, upper bound comes from that point on that curve, which has that equation. Now again, let's remind ourselves, what are we doing? We're looking for a y bound. It's a y coordinate. So in this equation, I need to solve for y as a function of x. Lucky break. Super easy algebra. I did that on purpose, right? We'll see some harder algebra coming up later. And that formula then gives our upper bound for y. Everybody good? Okay. All right, now I sliced dy dx for no particular reason. You can totally do it the other way. Let's do it the other way. Let's see what that looks like. Oh yeah, question.
Why don't you just take the volume of the square and then divide it by 2? Because it's a triangle.
I hear you, because this function it depends on the nature of that function, right? So you got to keep in mind, we're not computing the area of the triangle. We're computing some sort of an integral, and in this case, I think that would actually work, but that's a coincidence, right? In general, this could be some wacky function, and who knows, whatever, right? And so think of it this way. My favorite little physical metaphor is always mass, because it's relatable, right? And so is it always necessarily the case that the amount of mass in this triangle would equal the amount of mass in that triangle? No, of course not. There could be, the density could be higher down here and lower up here. So yeah, it doesn't work. Is that satisfying?
Yeah.
Okay. Yeah. Okay, so here we go. Slicing the other way. Y on the outside. Here's what our y slices look like. So there's our range of values of y. The first y slice, again, very often it's the outer bounds very often are just looking right at you. Our first slice is there where I'm going to say pretty clearly y is equal to 0. Right? I mean, it's the x-axis, so of course y is 0 there. And then the upper bound, another freebie. The last y slice there, that is literally a given point. That is 1, 1, the y coordinate of which is 1. So the upper bound of 1 also just for free. All right, now let's think about the inside bounds. And again, keep in mind, the inside bounds mean we're fixing a value of the outside variable. This then is our movement across that y slice, for which the lower bound for x is going to correspond to that point By the way, again, I can't emphasize this enough. Because the picture tells me. Right? You gotta have the picture tells me that it's that point, not this point. Gotta have the picture. So that point, which is on that curve, which has this equation. Now again, be careful. Don't move too quickly. There's the details matter. Very easy to lose track of the fact that I am looking for an x coordinate. Because I'm going in the x direction here. I'm looking for a bound on the x integral. So in this equation, same equation we saw on the previous page, right? Yeah, sure, of course, yeah, definitely. But here I need to solve for x as a function of y. Not y as a function of x. I need x as a function of y. And so my lower bound is y, not x. Everybody follow that? Everybody's happy? Easy to mess that up. So many students they get down to the point where they say y equals x, and I'm like, cool, x, right? And that's just wrong. Okay. All right, now let's look at the upper bound. Okay, well, big mess. Let me get rid of all of that. So again, on our y slice with y fixed, our upper bound for x is going to come from that point, which is on that curve, which has that equation, in which, again, easy to lose track, so let's remind ourselves, I'm trying to solve for x because this is an x coordinate as I move in the x direction, so I need to solve for x as a function of y, and so my upper bound is 1. Everybody happy? Okay. So, so one thing I'm going to point out, now we've got the same integral here, done two different ways. I did it, let's see if I can get this all on the screen. Yeah. So I did it dy dx. Whoops. Oh no, am I out of juice already? Oh, okay, well I gotta plug this in. I don't know why it works like that. Okay. Fine. So, let's see. Let's go back up like this. Here's what we got when we did it dy dx. Here's what we got when we did it dx dy. And do y'all remember when we were talking about when we had rectangular domains, I made this observation that you can do the slicing in either order, and you just do this. For rectangular domains, no problem. You want to switch the differentials? Okay, just switch the bounds. It's fine. No problem. Only for rectangles. And check it out. Here we totally did not get the bounds just switched. Yes, you can do the differentials in the other order, but the bounds don't do this. Yes?
For like the second point of that, like number 2.
Yeah.
Where it's x is equal to 1, could you not use the y equals x for that one too? Would that not be the...
No, you can't, because if I understand your question correctly, so this is all assuming that we have a particular y slice, so we're looking at this. The whole point is that we were looking for the upper bound, right? So we're asking what that upper bound is for the dx integral. And the upper bound comes from that point, which is not on, it's not on that line. See what I'm saying? So yeah, so that doesn't work. Yeah, okay. Cool. Okay, so yeah, two different options, and you do have to slice. You got to go through the process to see the bounds, right? No little quickie freebies like this anymore, unfortunately. Which way should you do it? Should you do it dy dx or dx dy? I'm going to show you several examples here that I've crafted to illustrate what I'm going to call tricks of how to make good choices of which way you should do your slicing. Should you do a dx dy or dy dx? And so let's just dive into those examples, and then we'll learn some morals of the story after we go through the experience. Okay. Now, by the way, time being a consideration, I'm not going to go through all of the details of every one of these examples. Right? We've got a process. And all you got to do is follow that process just like we did in the previous two examples. So I'm going to point to some particular points of interest in these examples, but I'm going to leave the rest of the bounds as exercises for y'all to think through. Again, give it a shot with all of these. Make sure you come up with what I've got here. If you don't, or if you don't know how to do them, come to my office hours. Happy to help fill in those blanks. Okay. So, first, let's talk about our domain here. We have this curve y equals x squared. We have this curve y equals 4. Our domain is bounded by those two curves. And I want to talk about what this phrase means, bounded by. This means two things. On the one hand, it means that these two curves make up the boundary of our region. And so, cool. I see a region there whose boundary consists of these two curves. But you know what else? I actually see several regions. What about this one over here? Right, if you look at this kind of infinite region that goes out in the sort of the first quadrant direction, that's got a boundary, and the boundary just consists of just the green and blue curves. Right? So, very importantly, that is not what bounded by means. Bounded by means also that the region is bounded. And what we mean by bounded is that it doesn't go off to infinity in any direction. We mean you can put it in a box. Right? And that region that I had over here, you can't put that in a box. It's too big. Right? So there is only one region here that actually is bounded, and furthermore, bounded by those two curves, and that's what I have in yellow. Right there. All right, so does everybody see why that is the one region that is appropriately described by that language? Everybody's happy with that? Okay, heads up, this is part of the question. Right? So it's part of your job, right, to interpret the question appropriately and determine what the correct domain is. Right? That's part of the question itself. Okay, so let's see here. Let's talk about the lower bound for the x integral here. There's a nice little point of interest. Here's me. Oh, I wanted green. As I go in the x direction, this is what my x slices look like. And my first x slice, to give me my lower bound, that first x slice corresponds to that point. Right? Here's the thing, that point is on that curve and that curve. Therefore, both of these equations. And so in order to find that point, we need to solve for x. Right? Solve for x looking at both of these equations. Now here's where a lot of students will make a mistake. A lot of students will say, let's see, y is two different things. Y is x squared and y is 4, so that means x squared is 4. So I guess x must be 2. A lot of people will make that mistake. It's a very common mistake. You got to remember, and again, high schools let you get away with all sorts of little math crimes, right? Every positive real number has 2 square roots. So all we can conclude from what we've written down here is that the x I'm looking for is either plus 2 or minus 2, and I don't know which. Right? So how am I going to decide which it is? Well, again, thank you, picture. The picture shows me that what I'm looking for is clearly negative. That I get from the picture. So of these two options that I have, negative 2 then is the lower bound. Everybody's happy? Okay. So you got to pay attention to that kind of thing. You got to make the appropriate choice. Sometimes the diagram or the figure itself is what helps you make the choice when you're trying to solve. Okay. The rest of these bounds, I think y'all can make sense out of. Make sure you can do that. Again, come to office hours if you have any questions. Okay. All right, let's look at the other slicing. Okay, same two curves. Right? Same region, all that. Let's see here. Y. There's our Y direction. These are Y slices. Right? Where's my first slice? Where's my last slice? Well, my first Y slice is at the origin. Thank you, picture. I need to know the Y coordinate at the origin. Well, that's a freebie. That's a 0. Again, sometimes you get lucky. Likewise, my last Y slice looks like that. I guess I could pick any point along that segment that I want, I suppose, but it's even easier just to say the slice itself is Y equals 4, where Y is 4. So again, freebie, right? So sometimes it's just staring right at you, and that's always nice. Okay, now let's talk about these inside bounds. As usual, we're going to fix. Oh, I didn't want the. Sorry. We're going to fix a value of the outside variable. Here's now how we move along that Y slice in the X direction. Let's think about this lower bound for X. Very common mistake coming up, right? That lower bound comes from that point, which is on that curve, which has that equation, and here's where the students mess up. So many students will then say, okay, I guess X squared is what goes there. And that's wrong, because they didn't follow the rules. Moving too fast and loose, not following the process. So what we need to do, you got to keep in mind, is remember what we're solving for, right? What we're interested in there is an X coordinate, because we're moving across this Y slice in the X direction. So I need to solve in this equation for X. You got to actually do a little bit of algebra on this one. So solve for X. Now again, not so bad, right? You solve for X. It's either plus square root of Y or minus square root of Y. Again, free information from the diagram. I can see that this lower bound I'm interested in is clearly negative. And so when I solve for X here, I get negative square root of Y. Everybody's good? Okay. Heads up for that kind of thing. Okay, now let's decide between these two different options, which one would we rather actually compute? Now, I don't know for sure. I don't know for sure because I don't know what F is and how the antiderivative of F works out with respect to either Y or X. That'll give considerations as well, sure. But most of the time, I mean, if I had to guess, I'd tell you what, I don't think I like this one. Right? Now, let me just be perfectly blunt as to why I don't like this one. Because I'm trying to figure out how this is going to play out, and this expression on the inside here, this inside integral, well, the dx antiderivative might not be so bad, but then I'm going to be plugging in square roots into my expression. This red inside integral is going to have square root of y peppered all over. I hate integrals that have square roots in them, right? Is it just me, right? Don't y'all too, right? These are hard integrals. We don't want to have to deal with square roots. So that looks like a nightmare to me. Yeah, in particular, the outside integral there, I'm scared that that's going to be a nightmare of an outside integral. So I don't want to do it. On the other hand, this inside integral here, well, it's going to have an x squared in it, but I mean, oh my gosh, I mean, not everything can be a constant, right? All else being equal, x squared is not that bad. I'm much more optimistic about the upper integral. Okay, so how do you tell in advance, right? I mean, before we figured out these bounds, let's suppose I didn't know what these bounds were going to work out to be, and I'm just looking at that versus that, and which one should I do? Well, you can kind of anticipate which one's going to have nice bounds and which one's going to have ugly bounds by just looking at the algebra of what's given to you in the statement of the question. And in particular, let's look at this equation. And now I'm going to ask, rhetorically. Would you rather solve for y or would you rather solve for x? Yeah, for sure. Definitely rather solve for y here, right? No square roots. If I solve for x, I'm going to have square roots. So make the choice that gives you what you want. I would rather solve for y, so I'm going to put y on the inside where y, therefore, is what I will need to solve for in terms of x. That make sense to everybody? All right. Now, this is not a guarantee. It's not always going to give you the best, most efficient answer, but 9 times out of 10 at least, right? Vast majority of the cases, this is going to point you in the right direction. Okay, next example. Now again, I'm going to do this slicing both different directions. We'll see what happens. We've got a triangle, various corners given per this picture. And y'all can do this one on your own, no problem. Make sure you can do this. Make sure you get these bounds that I've got here. And again, as always, if you get stuck, if you have a problem, inconsistency, whatever, come to office hours. Happy to set you up. But I think that's pretty straightforward along the lines of what we've done already. Where things get weird is when we slice this way. dy dx. Things get weird as follows. Let's think about the range of values of x. Well, x goes from 0 to 2. So it seems. Okay, well, here's the problem. In this case, let's look at what is the curve, for these values of x between 0 and 2, what is the curve that's going to give me my upper bounds for y? Well, that curve that gives me my upper bounds for y is that curve. And can I write down the equation of that curve? Not really. It's kind of 2 equations. It's one equation for the left side. It's a different equation for the right side. And I can't write a single equation. That make sense to everybody? Okay, so to avoid this super annoying problem, what I have to do is break this up into 2 separate pieces. I'm going to first look at what happens as x goes from 0 to 1. As x goes from 0 to 1, my upper bound for y is going to come off of that curve. That curve has an easy equation, no problem, solve for y, and you get that. All good. And then subsequently, I can look at these values of x between 1 and 2. For those values of x, my upper bound for y is going to come off of that curve, which again also has a nice and convenient equation that you can write down and again solve for y, and you get that. Conveniently, the lower bound is 0 for all of these, right? That lower bound is 0 no matter what x is. That's kind of nice. Okay, so that's how that slicing process worked. Now again, let's decide which one do we like. Would y'all rather compute this or that? I assume y'all are with me. We'd rather do that one, right? It's half as many integrals. Who wants to do 2 integrals when you could just do 1 integral? Weirdo, anomalous exceptions granted, of course, right? But most of the time, this is twice as much work. Okay, so next question. How do you know in advance? Again, I don't want y'all to have to just every time you do one of these, write it down both ways and then decide, right? How can you kind of anticipate and see it coming? So here's my take on it. There's different points of view on how to think about this. Suit yourself if you find a point of view you like better. Let me draw here. As I slice in the x direction, my slices start to look like this, and then something bad happens at that point, right? And then the slices kind of are qualitatively different because they have an upper bound curve that's a totally different curve. Okay, so the reason I got two integrals is because of the bad thing that happened right there. I'm going to say right there, right? Because that's where my upper bound for y sort of jumped from one line over to the different line. And so the way I like to see this, again, everybody's going to have a different take, no problem. I'm going to say I sliced through a corner. Right now, all exceptions granted, but most of the time when you have two curves that intersect, the fact that there was an intersection is why we had a problem here. Well, intersections tend to make corners, right? And so a pretty good little summary here is try not to slice through corners. And you can eyeball glance before you write down any algebra. You can just look at the shape of your domain and decide which way would slice through corners and which way wouldn't. So you can. We've already talked through that. As I slice like this, well, I slice through a corner right there. That's as I slice first in the x direction, right? Okay, so that's why we had a problem. What about the other one? With the other one, I don't slice through any corners. Now, I guess technically, this very first slice, yeah, that's right, I sliced through two corners there, but again, when you slice through a corner, you're going to have to just start a whole new integral. Cool, I was already starting a whole new integral there anyway, so it doesn't matter, right? And now you look at the progression as you continue to slice. Throughout the middle of our slicing process, we don't hit any corners. And then, okay, sure, fine, at the end I hit a corner. I was done anyway. Doesn't matter, right? So in the middle of the slicing process, I didn't hit any corners. And that's why this one worked out nicely, and that's why this one worked out not nicely. Cool? Yeah.
What if the x bound that we have here, the x2 was like closer to the corner? Would that matter?
Say it one more time.
If the x2, where we have the x2,
Yeah.
if it was like closer to the corner above, like the vertex above, would that allow us to still?
I don't understand what you're asking.
Like you say that when you slice like on the y-axis direction, when you get up there, like we were already done because what we wanted, like we already got. But then it's like if we had the second, like the last bound, the upper bound closer to the corner, would it still work? I don't know if that.
So I just don't understand. So we're not talking about this shape anymore?
No, it's the same shape.
Same shape. I don't understand because when you slice that shape, perpendicular to the y-axis, this is what the slices look like.
Yeah. So I'm saying if the okay, I'll ask you that.
Yeah. Okay. Yeah. Sure. Yeah. Okay. Yeah. Of course. No problem. Yeah. Okay. So So again, try not to slice through corners. Try to identify what's the variable you want to solve for. Let that be your guide as well. Good news, these tend to go in the same direction. So whatever, if you have a question where both of these considerations come up, they tend to point toward the same choice. Okay. All right. Next little awkward reality. Sometimes the domain's not given. So it's easy to see this coming from an example. So there's a surface. We've talked about this before. That's a paraboloid. Here's another surface. That, of course, is just a plane. And if we look at the volume in between, the volume in between is what I have there, which I think is easier to see over there. Okay, so we want to compute that volume. The approach I'm going to take on this is to slice up this shadow. Right? I'm going to think of that shadow as being my domain. I can chop up that shadow into a bunch of little pieces of area. On each little piece of area down here, let me draw the little pieces of area. On, for example, this little piece of area down here, I can talk about and talk about the volume sitting directly above it. And it's pretty straightforward to argue that the amount of volume then that you get of what I'm looking for, the amount of volume that I get is going to be the area of the base times that height. That height is the difference of these two z coordinates. And so that little volume is going to be the area of the base times this z2 minus z1 is that little height difference there. So the integrand of forming this argument of how I'm going to compute the given volume with a double integral, that's pretty straightforward. That's not that bad. But what's weird about this is, notice I do need to know what my domain is. And my domain, I just kind of vaguely wave my hands at, well, it's the shadow down in the xy plane of that thing. What is that? I don't know what that is. It's not given. Right? So you got to figure it out, and here's how we're going to figure that out. I'm going to point out that it's easy to understand this boundary curve of our domain. That boundary curve is directly underneath this edge of our solid. Yeah. That edge is where, let's see, let me get my colors straight. That's where this surface, which is this, by the way, that's where that intersects this surface. Right? It's where green intersects blue, and here's where a lot of students crash and burn. How do we understand these points here that are the intersection of these two surfaces? How do I understand the points that satisfy both of these equations? And so the following that I'm about to describe, I've seen a bunch of students do this. It doesn't make any sense. I don't know where it came from. I'm suspicious that there's a certain fraction of high school teachers that are promoting this. It doesn't work, doesn't make any sense. But here's what I see students doing. Students will say, well, I'm going to set these equations equal to each other. What is that? That's not a thing, right? And so students will say, I guess I want this to equal to this. It doesn't make any sense. That's not how equations work, for one thing, right? But also, notice how arbitrary it is. This 7 could have been on the other side. I could have subtracted that 7 to the other side of the equation. Wouldn't change the equation. Wouldn't change the plane that I'm describing about. But then the left side of the equation would be different. Well, which one should it be? Should the 7 be subtracted over here or not? You're going to get two different answers depending on what shouldn't matter at all. So it's sort of no way that could possibly make sense, right? Just another silly example, just for fun. I think most of us will agree that this is a true equation, and this is a true equation. Would I find where these facts are both true by setting 3 equal to 7? No, my gosh, what are you doing? That doesn't make any sense at all, right? Okay, so anyway, please don't do that. It just doesn't make any sense. There's no mathematical reasoning that makes that work. So what do you do? What is the right approach here? And let's see here. Let me, I wanted to erase most of that. Okay, so how am I going to understand these points? And it goes like this. For any given point down here in the domain, there's Z1 that tells you how far you have to go up to get to the paraboloid. Right? And then for that same point, there's Z2 that tells you how far you've got to go up to get to that plane. And that Z2, well, that's the Z coordinate of a point in this plane, so that's that. Z. Right? And now, geometric appeal, you got to just see this from the picture. The points that we're looking for, the boundary points that we're looking for here, so this sort of the purple perimeter of our domain is where the green height is equal to the blue height. right? We've got this lower surface and we've got this upper surface, and the edge is where they meet, where they both give the same z coordinate. So what we're going to do then, let's see if I can, what we're going to do is we're going to say, I want to know where this z is equal to that z. So you do have to solve for both z's. The one on the left is already solved for. That's nice. The one on the right, you have to do a little bit of algebra, no big deal. But setting that z equal to this z gives you this equation, and then you can do some algebra to get down to seeing that this is a circle. So we found what our domain is. Yes?
Could you please repeat why the two, you're equating the two z's?
Well, because it's just a geometric appeal. But if I want to know, where are the points that are on this boundary, that means I want to know where the distance up to the plane is the same as the distance up to the paraboloid, because I'm literally looking for where the paraboloid and the plane intersect, and where they intersect, they will have the same z coordinate, and so blue will equal green. Yeah, right. Okay. So anyway, sometimes you got to do a little bit of legwork just to figure out what your domain is in the first place. Now it still remains, and I'm not going to work this out because it gets a little weird and clunky. We've already served the purpose of this example, which is to find what the domain is. But you do still have to then take this domain and go through the usual process of slicing. If bounds come from points which are on curves, which have equations, solve for what you need, et cetera, et cetera. Okay, so make sure that you can do that. And by the way, I'm also going to point out, in order to get to the point where you realize this is a circle, and specifically which circle it is, notice we had to do that complete the square move. Do y'all remember completing the square way back when? My experience has been that a very large number of students in this course have forgotten, or might in fact never have known in the first place how to do complete the square. It's a very standard algebraic move. It's commonly misunderstood as only being needed for solving the quadratic equation, for which you can memorize a formula. So who needs it, right? And this is absolutely not the case. Completing the square, here's a nice example. Totally necessary in this example. It's got nothing to do with the quadratic equation. Okay, I'm going to say a couple of real quick words about 5.3. There's not that much happening in 5.3. It took me about 5 minutes to do this section in the other earlier lectures I gave. So I'm going to do this one in 3 or 2. Do this in 2 minutes. It's that easy. Sometimes you have an iterated integral dx dy, and you want to turn it into a different iterated integral dy dx. And again, you can't just do this. Those days are gone. Rectangles only basically never comes up. Okay. All right, so how do you do it? And the answer is really very straightforward. You just have to take what you've got here and take this integral and just reverse engineer and figure out what is the domain of a double integral that led to that iterated integral. And it's just undoing the usual process. So here's how that plays out. Y goes from 0 to 1. Okay, there's y equals 0, there's y equals 1. My domain must be between these lines because it says right here that y is always between 0 and 1. For a given value of y, now let me just switch down to here just to, since I have everything on here. For a given value of y, let's see here. For a given value of y, my lower bound for x, you can see right here, is x equals y, which is that line. My upper bound for x, it says right there, is x equals 1. That's that line. Right? So for a given value of y, apparently we go from light blue to dark blue, and so for a given value of y, we're going from light blue to dark blue, and what does that trace out? Well, that traces out this triangle. So now we have our domain, and once you have your domain, then you just slice it in the other direction, as you know, however you might feel like actually doing. Slicing it in the other direction in this case gives us this integral right here. So it's really not that big a deal. Now, why would we ever want to do such a thing? I'll just make a quick reference to the fact that this integral here, this inside integral, is actually not possible. And so sometimes when you have an iterated integral, it's algebraically a problem. So what this is, this idea of switching the order of the differentials, it's just a way to turn one algebraic challenge into a different algebraic challenge. And here, this inside integral now is actually quite a bit easier because don't forget, x being the outside variable now is a constant. So that's a constant. So all of that is constant, and it's easy to integrate constants. That's a pretty cool trick. All right, other little details to make sure you read. Y'all have a great break. See you on Wednesday. Don't forget about attendance if I didn't already get you.